And I would like to announce people from the NanoCommons project, so Dieter Meyer from Biomax and Tassos Papadiamantis from the University of Birmingham, who are going to show us for the next 2 hours the NanoExtract image analysis tools. To get into that, I would like to ask you to put some of your experiences or put some of your habits, how you actually deal with physicochemical characterization whenever you are ready to publish your NanoSafety study. So how are you doing actually, that we get a little bit an insight on kind of what people do. I mean, this includes our usual behavior too, of course. And with then we would like to start with this NanoExtract image analysis tool and with the NanoCommons knowledge base, where Dieter Meyer is going to give us an insight at the beginning. I remind you once again, and I have put this into the chat box already earlier, and also find the link up there in the dashboard, to, if you want to, that you provide one or several TM images that we can use for as an example in the next session. So the attendees are still filling this questionnaire. It's a very short one. It's just one question, actually. When I publish my NanoSafety study, what do I do? How far do I get my data into online available? So we have about 20% of people who have voted. It's of course anonymous. So I still let it run for a bit, that we get a little bit an insight and overview. Of course, you can answer give multiple answers. And I do see already here Dieter Meyer on the right in the video and Tassos Papadiamantis in the left in the video. Welcome, the trainers of the next session on the NanoCommons knowledge base and on the NanoExtract image analysis tools developed within the NanoCommons project by Nova Mechanics. I would also like to give tribute to Andreas Afantitis, Georgia Melagraki, Andreas Tsoumanis. We do have also a Zoom link to a breakout session giving you support. So you can in parallel go into the tool, you find it on the dashboard, and you get support. The Zoom link is there. I guess Andreas Tsoumanis is providing support there. Thank you, Lee Walker and Christine Balmer from the NanoCommons project from the UKCH for providing this opportunity with the Zoom link. And with this, I end the voting. We have about 30% of the attendees have given some insight into how they do that. So, I mean, quite a significant share of the people do obviously include quite extensive, or maybe, yeah, I would say extensive physicochemical characterization data into the nanomaterials that they used in their study. They also provide TM images, so this is obviously pretty common for primary size and shape information. And also they provide DLS or NTA or any kind of other data for nanoparticle size and agglomeration and suspension. They also do slightly less, of course, of people who provide DLS data for all the relevant exposure media. We heard past week also several talks touching upon the topic of experimental instances, where you can have these instance maps. But however, I mean, the relevant exposure media have an impact, of course, on the agglomeration of the particles. But then it starts becoming interesting. Upload into nanomaterial data online repositories. This is really not a very common way of doing. So people are aware of fairness, data fairness, but I mean, how to do this is eventually not so. We're not so familiar with this yet, and this is actually pretty cool because this is what we're gonna learn now in this session. So. Of course, the intention is to use a software in an objective way to be able to determine nanodescriptors, maybe quite extensive nanodescriptors from your TM images, and to do this then also in a way that you can upload data and can provide it to other people that could build on that. So I guess with this, we would like to start. Thank you very much for giving your very frank and open answer to that. And I switch to the presentation of Dieter. Or even better, he goes into the screen sharing. Please, Dieter, go ahead. And we look into how to access the NanoCommons knowledge base, how to upload TM images, how to create files there, how to upload them data from nano descriptor data, and eventually retrieve data from other people's TM images to be able to work on that and go into the models like Langtran has, for example, also touched upon in the previous presentation. Dieter, the floor is yours.
Okay, thank you very much, Martin. Can you hear me properly? Just micro check. Yes. Okay, great. Thank you. Okay. Yeah, thank you very much. This is a joint training provided, as you mentioned, by the University of Birmingham, TASUS, Nova Mechanics, who produced the image extraction software, and Biomax. We are responsible for the NanoCommons knowledge base. And just very brief introduction. Biomax is a bioinformatics software company. We are located in Munich. As you probably hear my accent, we are 20 years in business and have a global customer base and are about 50 staff, so quite substantial. Very, very brief background on the NanoCommons knowledge base, because it's different from maybe many projects in the sense it's not a data warehouse. It's really an infrastructure. NanoCommons is an European infrastructure project who provides services and tools to the nano community, to NanoSafety and nanotoxicology community. And the knowledge base is part of that infrastructure. And the issue it's working on, it's solving, is actually what we typically have in nanoinformatics, also in bioinformatics, where we originally come from, is you have a multitude of different sources. You have databases, you have files, you have images, and for every application, for every question, someone is building some integrative analysis pipeline. And that's great. That's working fine. You get your results. It does have some disadvantages. You have to rebuild your pipeline every time, and everyone builds their own pipeline, which makes it different, makes it hard to compare. And as Martin already mentioned, in terms of data fairness, that's also difficult. So what NanoCommons brings to this area is a concept that we call semantic modeling, where you have an intermediate layer that's giving you an abstract conceptualization of your field of interest. And that layer goes between all the different data sources and all the different applications. And that's what NanoCommons is doing. So the NanoCommons knowledge base really is building this intermediate layer, and you can see that as a mix of high-level concepts, ontologies, but it's not depending on ontologies. And then different user interfaces, different applications are put on top of that. So that's sort of a classical IT way of going forward, decoupling complexity and simplifying by providing an intermediate layer. And that's what we do here. And that's why today's training is really two parts. It's one part on navigating the NanoCommons knowledge base, and it's one part on the specific application, namely the NanoExtract image analysis. And just to get that in, really, what's the difference to a classical database is that if we have a number of projects here, if we have your project here, and you're thinking about managing your data and you don't have a solution yet in your project, then NanoCommons does provide you with a data warehouse. That's part of the deal. So that's one of the services. But if you already have your own data warehouse, so if you are using, let's say, the eNanoMapper software, the Embed software, or whatever, then what NanoCommons also provides you is with an interoperability layer that allows you to connect what you already have and integrate it with the community and make it available. And that's this interoperability layer, that's the semantic model, okay? So just as a bit of a background, and what's important is that this allows you to couple data and applications from very different places. So data that can be anything, particle characterization, that can be molecular data, omics data, classical toxicology, ecotox data. And applications, again, that can be anything. That can be expression analysis, network inference, that can be computational simulations, biomarker profiles, or as today, an image extraction tool. Okay. So that's the tool we're going to work with today. It's available at https SSL biomax.de NanoCommons. You have to register to go into the tool. There's an automatic registration I'm going to show you. And what it provides to you is currently about 500 different nanomaterials with FusChem characterization, with protocols, toxicology data, omics data. It provides you with in silico descriptors for those nanomaterials, corona predictions. It will provide you with groupings. That's one of the applications that we will bring in. And it also allows you to have in parallel public data. Right now, we have the nanomile data public and embargoed data. Right now, the nanophase data is embargoed until September next year. And it also provides you with a governance, with a possibility to access or ask for access to this data even during the embargo period. There's a data transfer agreement template, and you can look what's the metadata, so what is actually available and would you like to access. Okay. The services we're gonna focus today in the training is really the integration of the NanoExtract image analysis. So that's what I'm gonna show live in a second. And just to mention a few more services, there is data mining on the nanomaterials, on the data sets, toxicity data sets, and so on, particle characterizations. There is data upload. So if you want to use it as a data warehouse, there are ways to add your own data into the system and make that, say, the data warehouse for your project. And there is other integrated services. Just one example, expression analysis. That's based on RNA-seq data, where you can do differential expression, pathway enrichment, and you get your classical differential expression analysis. Okay. So, but now let's focus really on today's example. I'm switching to my browser. Hope that's working. Shared desktop. So here is your register button. You can automatically register. You're going to receive a mail that's giving you the access. All we need is a valid email. Doesn't have to be very institutional or anything. but that's what we need. And then the navigation within the system is on the left hand with a navigation menu. The entry page sort of repeats that menu. So you have your data access part here, where you have access to different particles, to characterizations, toxicity data, omics data, and so on. Also, as I said, nanophase, which is embargoed, and Mbed warehouses. That's one of the integrations where we actually interoperate with the existing warehouses. The data stays where it is in those projects, but those projects like eNanoMapper or NanoRec made their metadata available, so you can search that as well. Let's first focus on particles for a simple reason, because we need images if you want to do analysis, and that's part of the particles. And just to conclude the first page, you have the analysis part, where we currently have RNA-seq, corona analysis, and image analysis. And you have a part for ontologies, searching ontologies, browsing ontologies, putting in a natural language query and getting an appropriate ontology term. And all of these are available here. You have a help desk here and a help as well. So let's go for the particles. Let's view all existing particles. And this is also a common theme in this user interface. You'll see that a lot you have a page, a result page that gives you a list of results. And that's always structured the same way. You have the information, how many results you have. So it's 428 right now. You can browse the pages here from 1 to 18. And you can filter your results. These are in columns. So for every column, you can filter results as you switch the column. You can have multiple filters. So you could go for, let's say, description and the chemical element. You can actually show or hide different columns. So as you see, I was hiding samples and aliquots here because that's right now not important. And you can sort by columns. Okay, so you can, for example, sort by ID in ascending or descending way. Okay. And I'm sorting in descending way right now because the images that you want to analyze, they have to be associated with a particle in the system. And for today, there is a dummy particle. If anyone wants to upload an image and it's not part of the an image of one of the standard particles like the JRC or so on, then please use this dummy particle to upload your images. So that's the one to add your data to. You just go for the particle, you go for edit the nanomaterial, and that brings you to a page where you can upload your images just by searching and then adding an image. You can add a description, of course, and you can, of course, add as many images as you like by just inserting new rows here. Okay. And once done, you just close your page and the images are available. Okay. So that's basically how new information comes into the system. In this case, for the images, there are, of course, batch uploads available, not right now for images. Okay. So let me resort the whole thing again. And then let's go for the analysis. So we have the image analysis. And what we did is actually the image analysis is an integration of the NanoExtract tool built by Nova Mechanics. And the page you end up, if going for the image analysis, is actually the list of all images that are currently available in the system. You have the nanomaterial here, so you can again filter for your nanomaterial. You see your image that's uploaded, and then you have the ability to process, to go to NanoExtract and process your image there. And one thing I can also show here, this is a adaptive design. So if you have a small screen, it will adapt, and the columns that are lost, they're not really lost, they are available behind this plus button at the beginning of the column. So whenever there's a plus in the first column, it means there's some more information available. You can open and close that here. And so we can then go for the individual parts. So once you have uploaded your image, you have found it again in here. If you want to analyze it, you go for Process in NanoExtract, and that's going to automatically bring you to the NanoExtract software. And that's actually the point where I will hand over the analysis process and the training then to Tassos, because he's the expert in handling the software and in all the different parameters that you can optimize for that software. But maybe before handing over, are there any immediate questions? If that's not the case, then I'll stop sharing so that Tassos can actually start. And we'll continue with the knowledge base at the end of the analysis.
Please put your questions whenever they come to your mind into the chat box. We will take care that we get them to the trainers, even if they are not being aware of it immediately. So we will transfer them the earliest time point suitable. So far, no questions regarding the knowledge base, Dieter.
Hello everyone, sorry, just a minute to share my screen. Oh, come on.
This is within this short time that it takes. I would also like to remind you once again, make use of this opportunity today to eventually have a TM image hanging around, which you're not going to need for your next publication, and you would really like to check this out, how to work with it. Go to the chat, to the dashboard in the beginning, on top, and upload the TM image to the shared folder, and we can work on your example.
Sorry, it doesn't work suddenly. So, oh, Martin, did you put the presentation on?
I have put your presentation, the
Okay.
PDF version of your presentation, for giving some insight. Maybe the screen sharing is going to work later on.
Yeah, okay, thank you for that. So we can take it from there. So hi, everybody. First of all, I would like to thank Dieter for presenting us a quick overview of how the NanoCommons knowledge base works and how we can actually use the NanoCommons knowledge base to upload our data and also link between the tools so that we can, have everything kept together nice and tidy into one knowledge base, and also take advantage of the computational tools that are being continuously developed. So now I'm gonna give a quick overview, an overview of the NanoExtract image analysis tool, with which we can actually more or less take advantage of predictive methods and available algorithms. So we can actually analyze our TEM images without having to do it manually and save precious time in our day. So how the workshop from now on is going to work, it's more or less that we're going to have an overview of how the model was developed and the tool as well. And then the web service user interface, which is a very user-friendly, straightforward application. And then we're going to have some hands-on practice demonstrating some of the images that we have uploaded so that people can practice with using different shapes, and also some of the images that have been uploaded by the attendees. So an overview of what has been developed is that we use the ImageSafe features that are all the time being used to analyze TEM images and microscopy images, to develop a tool so that we can automate the process and have people using the tool to analyze their TEM images and not needing to actually go in and do it manually, as I already said. While uploading the images and analyzing them, you don't only have to calculate the, let's say, the nanomaterial diameter or the axis, if it's a rod, let's say, or a plate of the nanomaterial, but you can also get a number of other descriptors, in total 18, that then you can use in different other applications, either for further analysis, statistical analysis, or to load them into other tools, as we will show, and then do some predictive modeling and so on. And of course, the tool is available, publicly available to anyone, as you will see in this link here. So to develop the model, what we did is that we used 68 TEM images from 37 diverse nanomaterials. And when we say diverse, we mean different chemistries, different morphologies, and so on. And of course, and these images came from the NanoMile project, which we had full access to the data. So in total, as you can see, we used both pure metals and metal oxides. The metal oxide, so 27 pure metals and 10 metal oxides. And then we had, well, the majority of the images were spherical. And then we have rods, plates, and some other images that originated mainly from mating the particles, as we will see in the process. So what we did is that we used the same approach to develop the model in order to do the measurement of the different descriptors in the model development, which we applied in different types of materials. As you can see here, we used spherical, we used rods, we used plate-like, and we used the sea urchins, which these are Syrian nanomaterials that were aged in phosphate for around 21 days. And then we applied the methodologies, changing a bit, and then we changed a bit the filters that we used, the thresholds, algorithms that we used in order to develop the tool, and then applying all this to the images. So how the workflow works? Well, it's a step-by-step process. It needs a bit manual labor, and I have to say that it's based a lot on experience. So you actually need to work on it. You need to make sure to work the tool, and then as you work the tool and you work different kind of images that you will actually get, then you will get more and more experience, and more or less you will see that by time you will more or less know very quickly on the values and that you will need to use in each of the step of the process. So how the workflow works is more or less that you upload an image, and then you pre-process the image so that you reduce the noise that may come from for different reasons from the electron microscope. Let's say you have a lot of blurring, you did not focus well, and so on. So as to be able to create an image that can be better, and you can better trace and analyze. Then we have the thresholding step, in which you apply an algorithm and divide the image into more or less a binary image, and then in which case, in grayscale, in which case a part of the image will be turned to white and the rest of the image will be turned in black. By default, what happens is that above the cutoff image of the threshold, it will turn to white, and below the cutoff image, it will turn to black. And then, because usually what will be above the threshold image will be the nanomaterials, we do an inversion of the values so that the background will become white and the nanomaterials will look black. And then it will become easier for the tool to identify the nanomaterials and label them one by one. When you actually have an initial labeling of the nanomaterials, then you just start playing with the parameters so as to acquire the optimum labeling of the image that you got, to get the most out of the image, the maximum number of nanomaterials that you use, and in this way you can actually get a very good statistics as well in terms of standard deviation and so on. And then in the second to last step, what you do is you filter your image, more or less, because as we're gonna see in our test images, you may have some things that you would need to remove. Let's say like scales, or let's say if you have taken the image like through literature curation, maybe some letters here and there and so on. Or let's say you have some artifacts that cannot be labeled correctly, then you can remove them using filtering. And then when you're done, more or less, you calculate the descriptors and you get your results, in which we will see. You get an overview of the results in terms of average values, and also you can get your results in a nanomaterial by nanomaterial basis, and then go your results through more analytically. So to answer the first part of the question that was posted in the chat, so far, as I said, we calculate 18 nanodescriptors. So more or less, what we calculate is that because besides the diameter that you can see as the sixth parameter here, that people are the ones that are the thing that people usually calculate, you get a number of nanodescriptors like the surface area of the nanomaterials, the boundary size, the boxivity, which is like the extent to which a nanomaterial will look like a rectangle, the circularity, which is more or less whether it's a perfect circle or not, like a sphere or not, the roughness of the nanomaterial, and then you have some other parameters like the eccentricity, the extent. Again, these are parameters that will give you how spherical or how rectangle-like is a nanomaterial. And then you have the different other parameters like the major and minor axis, the minimum and maximum first diameters, which is actually the maximum distance between 2 points of nanomaterial, and the minimum distance between the boundaries of nanomaterial, the perimeter, the roundness, the solidity, and so on. So in total, all these parameters are being calculated automatically for you, also like as an average, but also on a nanomaterial basis, so that you can actually go through and use the results accordingly. Now, how this works. So the tool that we're gonna more or less use shortly in a hands-on practice, you use can you see my pointer or not, Martin?
Yes, Tasos, we do.
Okay, cool. So for more or less, you need to press the upload button, and then you upload like you could upload like anything, the image, which is loaded in the window on the right. And then what you have to do is choose a type of morphology of the nanomaterial that you need to analyze. So we have 4 options that you can use, which are more or less a spherical nanomaterial, a circular, a cylindrical that you use mainly for rods, carbon nanotubes, and so on, plate-like nanomaterials, and other, which more or less corresponds to more complex nanomaterials. Then the second part that you will need to do is whether to choose whether you will do the analysis with and without outliers or with outliers only. In which case, what happens in this case is that what you do more or less is that whether you will actually do the calculation using like, let's say, statistical outliers in the image, or you will just ignore everything and so on. And then what you need to do, which is very, very important, and I would like to spend some time here, is that as you see here, every image comes with a scale bar, which you need to identify. So what we need to do is to press the activate capture tick box, and then you need to draw a line into the image that covers the entire scale bar, and then input the number here, it says 50, into the box here in letter B, so that the pixels to nanomaterials ratio will be calculated by the tool and used for all other calculations. What I would like to point out here, which is very, very significant, is the fact that this is very browser specific. So whether you use, let's say, Firefox or Chrome, you will have a different behavior of the browser when you upload the image. So, for example, and this needs to be taken into account because the images that we take from the TMs are usually very large in size. So it will, in most cases, will not fit the box that is provided here. So how the browsers work differently, as we will also see in a hands-on practice, more or less what happens is that, let's say in Chrome, you will have the full sized image uploaded here, and you will have bars that you can scroll to move around the image. So you will always see a small portion of the image. So you will need to go where the scale bar is there and do let's say this process. On the other hand, if you use Firefox, what happens is a bit different. So in this case, Firefox automatically zooms into the image, so you will see the entire image. And in this case, there's a big danger, because it's not a full-scale image. When you actually perform the scale capture in a step, you will actually need to zoom into the image. So as we're going to see, when you do that, you will get a magnifying lens that will allow you, in this case, to actually zoom into the full-sized image and actually perform the scaling. If you do not do that, and you actually perform the scaling into the zoomed image, then your results will be totally off. So we will try to run an example like that so that you can see the difference in the values. But more or less, be careful very much when you use this tool, so that you always do the scaling using the full-sized image. From then on, from the next steps, you don't need to do anything. You will, and actually, in this case, in these cases, Firefox works better because you can see the entire image and the labeling and so on. So it's going to be a lot easier to use. So it's just a matter of preference. So the next step in the process is, I guess I put that twice. So, yep, sorry about that. So the next step in the process is to reduce the noise. As we already have said, you may get images that are not as clear as, let's say, the one that we're looking at right now, which means that they may have artifacts, they may have, a lot of noise coming from the background and so on. So what we need to do here is more or less reduce the noise by applying some Gaussian blurring. More or less what this means is that we actually blur the background of the image and the image in general, in a way, so that we can actually mask any noise and any artifacts that lies below the nanomaterials, so that we actually can make sure that we will not have any, let's say, miscalculations when we do the analysis. You can see whether you have done a good blurring or you need a better blurring as you move further down the tool, and especially in the next step, which is the thresholding and inversion, in which case you need to have a background that, as you see here, is completely white. If you see some, let's say, really minor dots here, black dots, or later on like some colored dots, then you need to go back and blur your image a bit more, because this means that these little dots will be taken into account, can be taken into account during calculation, and that will create a huge uncertainty and change your result dramatically. So please be careful that you see that your background is very, very clean. So what we do here, more or less, is, as I already said in the overview, we apply a threshold algorithm. So more or less, we divide the image into two, and above the threshold, we turn everything into white, and below the threshold, we turn everything into black, and then we invert the image. And so the result here should be something like this, more or less, a very white background with very black nanomaterials. There's a substantial number of filters algorithms that people can use. We will see application of some of them during the hands-on process. And I need to say here that it takes a bit of practice, but eventually you will see and understand that some of the algorithms work better with some morphologies, others work better with other morphologies. Some are very good for complex shapes, like, let's say, the H circuits and so on. And then you can use accordingly. And also, if nothing of this works for some reason, that you more or less have to pick the algorithm and run it, there's also a manual method of actually applying your own threshold values, which needs a lot of test and error to find the optimum number that you need to use. So we'll see. Then the next part of the tool is more or less to do the labeling and filtering. What happens here, as you can see, is that the tool will go and automatically start identifying the nanomaterials. As you can see here, the nanomaterials are identified and highlighted in different colors, so that the user can actually follow better the labeling process. And you can see that even, let's say, if we go back here, that you have, let's say, some overlapping here and so on, the tool has been able to more or less divide the nanomaterials. So here, what you can do is improve the thresholding, more or less how the tool will actually identify and divide nanomaterials accordingly. So you have 3 parameters that you can use, which is a distance merge threshold, and this will actually tell you what's the minimum distance to use in pixels. So all the values here are in pixels. Let's say if two divided segments are close enough, then these two should be merged together. So if you see, let's say, as we're gonna see in an example later on, that let's say you have a row that's been cut into half because the tool thought so, you can play with these values and actually say, no, this is one, and you need to merge it. Then we have the Gaussian size, which is more or less, again, it's a way to actually say to the tool whether to do more or less splitting. So the higher values that you put, the less splitting the tool will do automatically. So that means also that you need to be very careful, because if you go very, very high, or substantially high, then that means that more or less you will start getting huge aggregates in a way in your image, which is not what you want to do. So play a bit with that and get to a point that you have, let's say, the best splitting, but don't overdo it, so that you start, having nanomaterials that should be separate being split. And finally, the size merge threshold is again similar to the distance merge threshold, in which it tells you that that if something is has a size in pixel squared, more or less of this size, and these are close enough together, then these two should be merged. Again, this, let's say, can be used to merge again, let's say, nanomaterials that have been cut in half for some reason, and you tell it, and you cannot fix it with the Gaussian size. So you play with the size merge threshold so as to create a new nanomaterial and so on. And then the second to last step, more or less, is more or less the filtering step, which in this case, what happens is that we choose the minimum segment area and the maximum segment area in pixels, which means that we filter out anything that's below a certain value here, 10, and anything that's above a certain value here, 1000 pixel squared, more or less. And this means that we can actually remove outliers that do not really fit and will actually substantially change our results. So we'll say if you have, let's say, something like this here, an artifact or a huge plate out of nowhere, then you can use this so as to remove all these outliers and get a clearer image with more uniform sizes and shape. I have to say here, of course, that what people need to keep in mind is that this tool is very subjective and based on experience. So it's based a lot on the human eye, like you would actually analyze an image, manually, as people usually do until now. That you go in and you identify and so on. It does all the calculations automatically, but it's based on experience. And each, let's say, researcher using the tool may have a different approach into things, and pick somewhat different parameters. In which case, like some deviation in the results is to be expected, which is the case in any case when we're talking about experimental data. So, and the next step is that the tool will provide us with, let's say, an overview of the nanomaterials that it thinks are the best to use for doing the calculations, and we'll see the next results. But what I want to point out here is that you also have an option to perform statistical filtering. In case, as you can see here, by ticking the box. What happens in this case, as you will see, is that you will see that a lot of the particles that actually look a lot like those that have been kept have been eliminated. And what this does more or less is apply statistical filtering, calculating the standard deviations on all 18 nanodescriptors. And if, let's say, an identified particle here more or less deviates significantly from what has been identified as, let's say, the normal range, then this will be excluded. This has the problem, on the one hand, that if your nanomaterial deviates from the normal range for one of the 18 descriptors, then it will be eliminated. On the other hand, it's very useful when you reach to this point, and for some reason you are not able to have eliminated, let's say, things like scale bars because of, let's say, strong contrast between the bar and the background of the image and so on. So in this case, the tool here would actually pick all these things up and actually eliminate them so you can perform the calculations. But my advice and experience says that if you get to a point like this, where you see that more or less all these nanomaterials look the same and look that they are in a let's say, in an acceptable range, then you should not use statistical filtering, because then you will lose statistical, let's say, significance in terms of, let's say, of your replicates, which is going to be based into one single nanodescriptor and keep only, let's say, very few particles that actually fit all the ticks, let's say, statistically. So then the tool will provide us with the results after having done all this. So the tool will, as we're gonna see soon, will give us like a table that has the averages of all the descriptors that are being calculated by the tool along with the respective standard deviation, and you can actually also see how good the analysis has been in terms of, let's say, monodispersity and so on. You can also as you can see here, you can download these results in the mean values into a CSV file, which you can load into Excel and analyze more. But you can also download the results for each of the separate in a nanomaterial per nanomaterial basis. So more or less, what this does is will give you the values that have been calculated for all the nanomaterials separately, which you can download, and then you can actually also play with them, do your own calculations. If, let's say, you have not been able to remove an artifact, you can actually identify it and, let's say, remove it and run again the averages and so on, and then get the results. And as I already said, and more or less here you're done. And as I already said, and I will demonstrate these examples later on, that the tool can be used in very complex images as well. So let's say if you have, let's say, plate-like nanomaterials, as you can see here, I believe this is zinc oxide. So you can actually identify, different plate sizes, and then you can choose to keep, let's say, one of the biggest plate and analyze them. But most importantly, when it comes, let's say, to serial nanoparticles that have been aged, let's say, in phosphate, as this is the case here, you can see this characteristic C-Erkin shape that's been acquired by TEM and is due to aging. In which case, you can actually use the tool, taking good care to play a lot with the parameters and actually analyze the image and get some results out of it. Actually taking into account the C-Erkin shape and so on, as you can see here, which actually will give you a better understanding of the roughness and the surface area of the material as it has been captured by TEM. So we will go through these images together as well. And then to answer the second part of the question of how do you utilize these descriptors that you calculate for model development, is that we actually have developed two predictive models to calculate the zeta potential of nanomaterials of nanomaterials. So the first tool that was developed along with NanoExtract is that it takes into account more or less the main elongation that's been calculated by the NanoExtract, and then what you need to do is to tell the tool whether it's an oxide or a pure metal. The pH, here we provide two pH values of 6.7, 6.5, and 7. And then you add the main elongation as has been calculated by the NanoExtract tool. And by executing the computations here, you will get an estimate of the nanomaterial zeta potential in this case, using the main elongation. And the other tool that's a bit more complex, what it does, it utilizes 5 descriptors. 3 of them are molecular. More or less, these are descriptors that you can actually calculate or find using the periodic table and atomic parameters of the nanomaterials. So it's the metal ionic radius used to create in the nanomaterial, the sum of metal electronegativity divided by the number of oxygens that are present in the nanomaterial and the absolute electronegativity. So you can find these values, a range of these values inside the tool, so you can get them ready more or less. Then you just input what material you want to analyze and whether you have a coating and the type of coating that you have. And then you can use the diameter as has been calculated from an extract to actually predict or estimate the zeta potential of the specific nanomaterial in water, which is a more detailed approach. The other thing that you could do is, let's say, to go and prepare your own workflows and add all these descriptors in your data set as an enrichment, so that then you can actually perform a full model development, so to see whether any of the descriptors calculated from an extract plays a significant role when it comes to nanomaterial behavior, let's say. For example, let's say if you have the Sierkin shaped nanomaterials here, maybe the roughness, the high roughness, will have an effect on how these interact with, let's say, cells and so on. And this is all for me, from me for now, on how the tool has been developed and how it's been used theoretically. And I'll be happy to answer any further questions before we move into a hands-on practice on how the tool works. So thank you very much.
Thank you, Tassos. Let's give it another trial with the screen sharing. We have meanwhile obtained a few more examples in the Google Drive, in the share folder. Basically, there are 3 folders, new folders, where 10 images of participants have been deposited. Thank you for that. That's great. You can really apply it on your examples. Yes, it's still 3 folders.
Can you see my screen now?
Yes, now we see.
Okay. So do you see an extract tool?
Yes.
Okay, perfect. Okay, give me a quick second, please. To move things around a bit. Do you still see the nano-extract?
Yes.
Okay, perfect. Okay, cool. Thank you. So this is an extract tool, more or less. As you can see, it's now nothing has been loaded. So as I already said, we started with the demo image, which is very straightforward to analyze and play a bit with it. So as we already said, what you first need to do is press the upload button, and what you do here, you pick the example and open it. Okay, so now you get the image. What we need to do now is to so first of all, we see that we have an image that has mainly spherical nanomaterials. We have a rod or plate-shaped nanomaterial here, artifact here, which we will need to eliminate. From the options, we pick the circular and then activate capture. And then we have here the scale bar, in which we go and draw a line to cover the whole scale bar like this. And then we give the scale length, which is 50 nanometers, and then we deactivate capture. And as you can see here, it calculated the line length in pixels, what's the measured length that we gave it, and calculates the pixels to nanomaterials ratio. And then what we do more or less, we can do a test run that's going to work in this case. We press the computation button that's here on the upper left-hand side, and is being processed, the image. takes a bit. So here, as you can see the image here. That's a bit that's clear, more or less, as taken by the TM. And here you can see that there is some blurring applied in the image, so as to remove any noise that may be in the background, and you still have the scale bar here. And then you see here that the thresholding has been applied very well. You have a very clean white background, and you have an image, different nanomaterials being turned into black. You also have this artifact here that's more or less a plate or a rod. But you can also see that still here you have the scale bar that still remains. And also you can more or less barely identify the 50 here that remains. And here you can see that more or less you have the labeling of the nanomaterials. As you can see, we have a very good labeling, although this is a very good image. But you can also see that you have here some parts of the image that have been identified, let's say here, more or less, that have been identified as one nanomaterial, whether it's more or less aggregates of nanomaterials. And also here you can see what I told you, that it has taken the rod-shaped nanomaterial and has split it into, let's say, 3 different nanomaterials. And then again, with the you see that with the labeling improvement, more or less with the default values here, you get a very good labeling of the nanomaterials. And eventually, when it comes to filtering, because we apply a lower and higher cutoff value, and as you can see that the nanomaterials more or less are within the same range, then all these artifacts here, like the scale bar here that has remained and the big artifact here, have been removed. And then you are left with a number of nanomaterials with a very dark background, so we cannot see any, let's say, dots that may affect our results and so on. And then you get the results, in which case you get the diameter of around 20 nanometers, which is correct for this type of nanomaterials that we used, and all the other values. So the thing is that, let's say, if we play a bit, so let's say, as I told you that, let's say, if we change the Gaussian size, that it will lead to less splitting. So keep an eye on this image, and how this will work is that if we run it again by increasing the Gaussian image, the Gaussian size, then when it finishes, so when it finishes, you can see here that things became a lot different. Okay, in which case this might be a bit better, but that's a different story. So here you can see that here now we have less splitting. So we have the full artifact here, as you can see, but also we have more aggregation in the nanomaterials, as these have been identified, because we told the image, the tool, to do less splitting. And in this case, as you can see again, we move forward, and then eventually we'll get a good splitting, because by applying the cutoff values, you can remove anything that's more or less that doesn't look right, let's say, like that. That's like large aggregates and so on. And again, you can get the results, and you can see that we have a small change in the diameter, let's say, of around 0.1. That has an effect on our results. So by playing with, let's say, these values, the splitting and the thresholding and so on, you can get a very good splitting. You can get a lot of results out, and so on. And then you can get, let's say, the maximum here, the maximum number of nanomaterials identified, and get a very good standard deviation when it comes, let's say, to what when it comes to reporting how many, let's say, nanomaterial replicates you use to produce your results. I'm gonna, okay, so this is it for more or less. This is a very straightforward image. So the next image that I would like to demonstrate is a rod-shaped, that's wrong, sorry about that. So again, I'm gonna use a pretty clean, straightforward image. So here, what you see is more or less rod-shaped nanomaterials. So these are gold nanomaterials. How we approach this, more or less, what we will do now again is that now in this case, we will use the cylindrical nanomaterials, again with and without outliers. Here we see that beside the scale bar, we also have this A letter here that we will need to remove in the process. Again, we activate the capture we activate the capture, we tell it how much it is, we deactivate, and now we have this. So now let's try to run the image using the default values as we did with the silver nanomaterials we did in the previous example, and see what we get. Okay, so here, as you can see, we have images here. We have identified the different nanomaterials identified. Not so good. We still have the A and the scale bar. You see here we have a pretty good thresholding and inversion of the image. Again, we cannot see any, let's say, background artifacts and so on. And here things start to get a bit bad. So as you can see here, you have a lot of splitting for the nanomaterials. Which means that here as well, we have aggregates. We have the rods being split into 2 or 3 parts. And then eventually, let's say when it comes down to it, you see here, we have this problem here, although the scale bar and the A letter have been removed. But as you can see here, instead of having full rods, we have, let's say, half of them and so on. And although we got some results, these apparently are not going to be correct. And in this case, what I would like to advise you to use in this case, in most cases, is these values here. So the major and the minor axis, well, more or less, is going to be the length and the diameter of the nanomaterial, and the maximum and minimum for its diameter. That will give you more or less the same. So now let's go and see how we can fix this image. One of the problems that we see is that when it comes here, is that more or less we have a lot of splitting that is being done. And also we see that that we need to do less splitting. We will try to increase the Gaussian size to see, let's say, whether we can correct this as much as we can, and then based on what we find, we may change the distance and the merge threshold, and the size threshold, so as to again to either create some more splitting, let's say, when it comes to nanomaterials that are very close to each other, or to actually divide the ones that are split while they should be as one nanomaterial. Takes a bit. Okay, so now, as you can see, we got things became a lot better. You see that we have now a lot less splitting. Still, some splitting exists. So we'll try to also fix that by playing with the distance, the merge threshold. So you see that while we had a lot of splitting in the previous case, now we have a lot less. Still, there is some, and we have some aggregates. So what I'm going to do now is I'm going to, let's say, increase the distance threshold. So merge threshold, so that trying to make this, let's say, particles here to merge as much as possible, and also the size threshold, so that you know, it will more or less pick these larger areas to merge together and see where we get. Okay, now as you can see, and now you see here that things by changing these things became a lot better. So now more or less we have a lot less nanomaterials that have been identified, while we started also dividing these ones here. And eventually, if we go, let's say, to our calculated image, besides these two here, in the small part here, more or less we have full rods that have been calculated. So another thing that we can do to see whether things can become better is change the thresholding algorithm that we use. This can play a huge effect even if you think that you know, a material works really well with a specific algorithm. So based on experience, I have found that these two, the minimum error and the minimum, work pretty well with nanorods. So let's say by picking the minimum error to test and computing again, takes a while. Okay, while this is being calculated, let me show you, let's say, this complex image of the circuits. Okay, so here you see we have this image of the edge nanomaterials. You see here the scale bar because the image is borderline fits the box. So you see that these were spherical nanomaterials that have been aged in phosphate and have taken this circuit shape. So in this case, it's pretty hard to identify whether you know, the size or the roughness or the surface area of the nanomaterials. So in this case, what we're going to do is gonna play with the parameters a bit more and the algorithms, so we can actually get a good estimate of what has been of the different parameters. So here it failed. So I should not have done that. So here, using the minimum error gave us an error, which means that in some cases you will get an error when you run an image. And by reading the error, it will tell you exactly what has gone wrong. So it will tell you whether you need to change the filtering parameters or the thresholding algorithm or something like that. So then you will need to go and change it again. And of course, you will get nothing out of it. Okay? So going back here, so now, of course, we cannot use for these nanomaterials the spherical, the circular shape nanomaterials. So we'll go with other. Again, in this case, you see that this is grayed out. So this has a default value that you cannot change. Again, we need to identify the correct scale bar. And here, as you will see, is what I told you, that you see a magnifying lens. And this is why, because the image does not completely fit the box, so we will need to transform it into its full size to get the correct scale. Theoretically, we could actually do it here and get a scale value here, in which case the results would be off. So it's better not to use it. So by clicking here on the magnifying lens, you see it goes to its full size. The scale bar has become a bit bigger. But now we are confident that we have the correct scale that we can get from the image. We add the scale. Remember to always put it in nanometers. So here it says 0.5 micrometers, but we need it in nanometers. So make the unit transformation. We click, and then let's say if we do the computation using the default values, we're probably going to get an error. So going back here, using the minimum threshold, now you see that we have a better, let's say, result when it comes to the labeling and everything of the nanomaterials. So in this case, and if we go down more or less, you still see some, let's say, half rods that have been identified. But in general, you see that using the minimum threshold give us a slightly better image than the one expected. And so now to cheat a bit, I will add some pre-prepared values that I know work best. So by changing the minimum segment area here, as I have told you, more or less what I'm going to do is I'm going to remove all the halves that may remain and keep only these nanomaterials that are full rods and so on. And as I said, this comes like with experience, so that you will know that by working on specific images and knowing how specific images work, then you will be able to more or less do it a lot faster because you will know more or less the ranges in which you need to move and so on. So here, it has finished pretty fast. You see that even with these values, you have some labeling and so on. And it can identify in a way the circuits and then give you some results. Now, one thing that I want to say here is that a very powerful algorithm for thresholding is intermodes. So in general, what we have seen is that using the intermodes algorithm works pretty well with complex shapes. Another thing I want to point out, as you will see here, we have here some small dots that you can see that they are being transferred here and so on. So these things can affect our results. So what I'm going to do is I'm going to increase the blurring slightly so that these here small artifacts that you can see are removed. So again, keep in mind that, and we press computation. Jumping to the other one. So now, here you see that by using the pre-prepared values, more or less, you have a very good splitting of the nanomaterials. You see that you have very few, I think there must be 2 or 3 that are split when it comes to the rods. And eventually what you get is a pretty good rod-shaped nanomaterial, nanomaterials. Then you can get the results out from. And then you're free to play. I'm sure that you can more or less play better and make it slightly better if you want. So the images are uploaded so you can play with them. But more or less, this is the process on how you actually deal with rod-shaped nanomaterials. And here, as you can see with data modes, we have some good splitting, and then we have now, as you can see again, some artifacts here, and so on. So again, by playing a bit, by doing some proper filtering, and so on. So this is less splitting, yes. So by filtering a bit on the nanomaterials, so as to remove, let's say, these parts here, and compute you get some, okay, this needs a bit more working. So you get, let's say, you see the circles here. I need to increase the thresholding value, the filtering value a bit more to remove this. But then eventually we will get a decent estimate of the circles, let's say their diameter, the minimum and maximum for its diameter, which is the longest and the shortest distance between the boundaries of the nanomaterials, and also the good things that you can get a good estimate of the perimeter and the roughness, roundness, and so on. So these are the examples I would like to run to begin with when it comes to the pre-made images, complex images, before going down to the images that you have uploaded. So are there any questions so far on the tool? What's your opinion? Is it easy to use, hard to use? And is everything clear on how it needs to be used and so on? So 2-3 minutes to take any questions that may exist.
Thank you so far, Tassos. There was one question, but you came back to this question. You saw it yourself. This was very early regarding the nano image descriptors. So far, no further questions. Please put questions if you have into the chat box. Tassos is ready to answer them.
I see Christoph typing, so let's wait. So I will also try. Yes. Thank you for this question. It's a great question. I would say that in general, yes, we consider this still representative because, as you said, it's we can actually get to more than 50% of the particles in an image that can be acquired. And keep in mind that we're trying to think pretty fast here. And taking into account that if you have, let's say, an image like that, that more or less you expect to find that more or less things are the sizes are more uniform, let's say, then getting, let's say, 50% of the materials will give you a good estimate of the image. Of course, you can always play with the parameters to go into more depth and more, let's say, detail in terms of what you used and the algorithm that you use to maximize the amount of, let's say, of nanomaterials that you can identify and measure. But in general, yes, we consider it to be a pretty good representation, statistical representation of what has been identified. And I would also like to remind you that in general, when you analyze a nanomaterial, then you use a set of images to analyze for a specific nanomaterial, so as to get a pretty good standard deviation from let's say, different areas of your sample. So by, let's say, running 3-4 images of the same nanomaterial, but from different areas of the sample, then even by keeping 50% of, let's say, the nanomaterials that are present in an image, then you will get to a very good statistical outcome when it comes to the number of nanomaterials you use to produce the results. I understand that, like, ideally you would be able to get all the materials from an image, or most of the materials of the image, and just remove the ones that didn't more or less make sense, or you would be able to load a number of images at the same time. But in this case, I believe that by running 3-4 images from the same nanomaterial and different areas of the sample, then you get a very good statistical outcome when it comes to the analysis. Manually, like, if you mean, let's say, to click on it and remove it, I would say no. But I would believe it would be pretty hard to come to the let's say, to the last step and having kept something like that. But it can happen. In which case, then what you do is you use the automatically remove outliers. In this case, what you do, if you click on the automatically remove outliers, you see that you remove a substantial part of the image, because, as I said, what happens here is that it will remove all let's say, the identified morphology nanomaterials that do not fit all the let's say, the statistical normal range as the algorithm assumes to fit. In this case, everything that you see that does not really fit will mean that it will be removed automatically. Else, as I said earlier, if you see something that doesn't really fit, then by playing with the minimum and maximum segment areas, you then most likely can remove it. But if you're so unlucky that you get somewhere that, if by using anything, then use the statistically processed image and results. So in which case you will apply statistical filtering, and everything that doesn't make sense will be automatically removed. But you will also remove some of the parts that, some of the nanomaterials that should be there. But let's say they may have, let's say, the aspect ratio might not be the perfect or something like that, so it will be removed as well. Or in the worst case scenario, you can more or less keep it as it is, download the results, and then identify the morphology that doesn't make sense, delete it from the full results, and then in Excel just do a quick calculation of the averages and the standard deviation. But that's a good suggestion, and I think that we will look into whether it's possible to more or less find a way to apply that to manually remove artifacts in the last step of the image.
Okay, thank you very much, Tassos. So far, no further questions as I see in the chat. So we probably close the question and answer window again. We have, however, at the moment 3 example folders in our Google Drive, the shared folder. So each of them containing a couple of different images from titanium dioxide over nanoseria. Silica nanoparticles are there. This is, of course, really a jump into cold water, and we really appreciate having a volunteer like Tassos to try out something like that. But we can eventually look into some of the provided examples and give it a trial. And eventually come up with a couple of new, pitfalls that may arise, like understanding some of these settings and some of these default values, and discuss them actually. So the shared folder was again shared by Andreas in the chat box.
Yes, give me a minute to. I'm going through the images because I haven't seen the images that have been uploaded today. Okay. So. Okay, so. Okay. Okay, I'm gonna start with the ones that I have. It's actually, I would like to thank Ingrid because these images actually give a good overview of some of the bottlenecks that people may encounter when it comes to nanomaterials. So we have this image of, I'm not sure what material this is, to be honest.
This is silica.
Silica, okay.
Silica nanoparticle with a coating of, I guess, undecanoic acid or something like that. So it says COOH.
Yeah. Okay. So let's say here you see that although it's theoretically a very clean image, you have a strong contrast in the scale bar, but you also have these nanomaterials here that apparently decided to sit their own way. You have overlapping here and so on. So I've not been able to work very deeply on that. So, but I have an idea of how this should look. In this case, and feel free to also use, the tool while we do it here as well. First of all, we know it's spherical nanomaterials with and without outliers. We activate the capture. And again, here, I cannot stress this enough. Remember that to get the magnifying glass, to make sure that, because you see the difference. So I wanted to run this image, that's why I picked it, so that I can show what can happen if things go very wrong, if you don't do the correct scaling. So we pick the scale, we can tick, and then, wait. Okay, let's run it with these settings now. We'll probably get an error here. We'll see how it goes. And also, I would like to run the same image, but making the mistake of not actually identifying it correctly in terms of scale. So as you can see here, the thing is that, you know, the magnifying glass is here, but if you go a bit higher, you may not get it. So I will do it, let's say, assuming that this is the correct one. So you can see to begin with that the difference. So here you have a pixels to nanomaterials ratio of 2.785, and here you have a 0.835. So you can understand that what we're going to get from here is going to be totally wrong, and probably we're going to get nanomaterials that are huge compared to what they actually are. So here you see we got an error that says successful execution was possible. Please check filtering parameters or change nanomaterial type or combination or both. So let's see where it's stuck. So here you can see that the threshold in the inversion is not really good because we don't have well identified nanomaterials. So you can see that you have a lot of roughness, like you have a lot of, you don't have clearly defined edges, which is then gone down, and you see the splitting here is very bad, and so on. And eventually it identifies more or less nothing. So when you see that, a good thing to think of is that if I see that I don't have clearly defined edges, then probably my first holding was not good. So the thing to do here is start playing with the parameters. As I already said, the intermodes or the minimum error algorithms are pretty good for things like that. So let's try the minimum here, and I will not touch any of this for now. No problem, it's going to work. And see what we get. At the same time, I'm going to do the same here. Okay, again, we could not successful execution. You see, we got a slightly better now identification of nanomaterials. Again, we could not get the correct values. So what we can do next is more or less change how things are. Let's say the splitting. Let's try to split a bit more. Okay, here. Again, but let me change to the minimum error. Compute. You see here that when you get to this part, it still identifies the scale bar because It's in white over here. Strange. So again, it doesn't work. So I'm going to try and increase, because of the size of this, I'm going to try and increase the area that it uses to calculate, like to increase the area that it calculates, that it finds things. Because as you can see, we got a decent separation here in terms of nanomaterials. And you can see here that this part here, with the nanomaterials, which I still don't understand how they managed to stay like that, are more or less identified here. So we would be able probably to remove them. Okay, while we play with that, let's see another image. So here you see we have this part here. That's the edge of the sample or something. We have a lot of nanomaterials that have been that have been, that cannot be really identified. So what we're going to do here again, we have a circular nanomaterials. Again, cannot stress this much. Be careful with the capturing process. In which case now again, we will try to run using the default values, probably fail, and so on. Again, so if you get a lot of this, a good thing to do is to try to blur the image more, because you can see here with time it has become a bit, although you make the images a lot sharper, you can always get a lot of background noise suddenly. So by increasing the blurring, sometimes may help a lot with what you're trying to do. So let this run. This runs as well, and I will try to see one of the other images that have been uploaded. So this is another image that was uploaded today. That's going to be a very interesting image, to be honest. So these are plates. I would be more comfortable to use Chrome for this image, to be honest, but let's try. So in this case, I will increase the blurring. So we'll use the intermodes to begin with because they're pretty entangled together and so on. So let's see what we get from here. Oh, come on. Okay, so here, well, you can see you have some results, but they don't look really good. Again, what I'm gonna do is I'm gonna increase, so here you see a lot of background. So I'm gonna try to increase the background a lot. I'm gonna use the minimum error. I'm gonna try not to merge at all as possible and increase that. Okay, and let's see what we get here now. Does make sense. Okay. Okay, we need to fix that a bit more. Put the background here. It may take a while for this to run. Okay, let me. Okay. Okay, apologies about that. Apparently, I'm increasing here the I love the background because I wanted to I want to cut the top right corner where it has the the sample edge that has what I take is the sample edge. Let's run this now. Yes, I'm sorry, I think that the tool was stuck. That's why it was not working. So here you can see now that we have a pretty good, clean inverse of the image. You can see here that it identifies things. Here is the part that's the most problematic, and eventually we get, let's say, part of the images of the particles here. So it's an estimated diameter of 86 nanometers. I don't know, Martin, if that fits well. So you see that it identified. Of course, by playing a bit better, So this was something that I did very, very quickly. You can actually more or less get, you can try and remove these parts here, and then keep, let's say, all the surrounding ones. You can see that it even identified, if you remember the image, this part here, although because of the difference in intensity here, it identifies, the different things. So we got a decent outcome. So I'm going to use the same values to run this one, that the scale bar is totally wrong.
There was one question in the chat, Tassos, regarding the error. Was this because the system was stuck?
Yes, probably. Probably, or maybe I was running too many images at the same time. Yeah, but it's more about, but I think it's because the system is stuck, and I really apologize on that. So. As you saw, when I refreshed, it's like it could not load the image. Try this as well. I'm sorry, I don't currently look on this side. So if you see that this error that I have, what you need to do is refresh the tool, more or less. Probably the code is stuck or something, and so on. So hopefully now it functions well, because as you see, I tried to upload an image and I could not upload it. So probably there was something with the bandwidth or something. So if you refresh the tool, it should work. Yes, I believe that it's because many people are now trying to also use the tool. So probably it makes the system get stuck. And I think that's because our technician, lead technician Andreas, has put a limit on the workload that can be applied on the algorithm, so as not, because we use the NIME platform, the Freenet platform developer tool, so as not, let's say, to over bandwidth the tool. So I really apologize about that. So if you got something like that, it's the first time I see it, to be honest. So try to refresh the tool, and then it will probably work. Cool. Okay, so this worked. That's good. So if you remember here, we have this area here that we wanted to get rid of. So we did a lot of blurring. Again, you see that we use the minimum error. You see that we have a good overcome, and then we come down here, and then you see that initially we don't have a good splitting. You have a lot of aggregations and so on, and eventually, by playing with the values, we have managed to create the splitting, decent splitting. Again, which you see here the artifact, but when it comes down to the final, let's say, image, all these things that don't make sense usually has been filtered, and we are left with around 20 nanomaterials, and then we get the results that we need. So you see that by going in and playing even with nanomaterials like that you have some substantial overlap between nanomaterials or even artifacts because of the sample, you eventually can get a good measurement out. And again, as I said in a previous question by Christophe, by analyzing different areas, you can, like 4 or 5 images, you can get to a good number of statistical significance when it comes to nanomaterial number to use for your analysis. Still stuck here. Okay, let's see what's happening here. Okay, I reloaded that. Plates. So. See, like I could not see it before, but now I found that it actually has the magnifying lens. So, and they magnified. So if you want to make sure that you don't have to go through this and and something goes wrong with the scale, I would suggest that you use Chrome to run the tool, that the image will not automatically zoom. Or what the other thing that you can do, it's more or less you can go in and use Firefox to run so that you can see the entire image and then be able to identify the correct settings to analyze your image, and then transfer to Chrome to validate your results, to see if with the exact same settings, if you get a good result out, and so on. Let's see if this works. Okay, a bit better. We start getting some divisions here compared to the thing. Come on. Okay, any questions? Well, because you're coming to the end of the session, and I don't want to take your time, and I apologize for the technical issues that we encountered. I was hoping to be able to run a few more images. So are there any more questions that you would like to be answered? No, you can use a number of formats. So JPG, PNG, so other image formats are you can use. It's possible to use. So so if you see, let's say in my case, so which one was that? So here you see that this one, the H serial were PNG files. Also, the gold was PNG. So you can use a number of formats. So that's up to you, which format of image you would like to use. But this has a lot to do with what you do. So people usually prefer to use the images as they get them in TIFF format from the TM.
Well, thanks a lot, Tassos. This was definitely a jump into cold water.
Just a second.
Try out with many things at the same time.
Martin, sorry, there's one more question by Sebastian. So Sebastian, do you see the scale bars on the right and bottom hand side of the image, like here or below here? So you need, if you see the scroll bars, just scroll to find where the scale bar is, and then you will be able to draw the line. So I assume you're using Chrome or some other browser, or try to switch to Firefox and see if you can see the image and then zoom in. You cannot do the data analysis offline, so more or less you need to do it online. You can access the tool either directly through the URL that we showed here, or through the Nova or through the NanoCommons knowledge base by uploading the image and pushing it there. If you want to, let's say, analyze 4 images separately, then yes, you would need to download the results and let's say merge them and then do the averages and so on. But we will implement in the NanoCommons knowledge base a function so that, let's say, you gather the results from all the images, and then probably there you would be able to get an average from all the images.
This was actually also a very good comment. Dieter was also suggesting that we somehow wrap this now also up in conclusion to how this is going to be done if it is started directly from the NanoCommons knowledge base.
Yes.
I would like to invite Dieter to also participate now in kind of how are these generated nano descriptors then captured in an automatic way in the knowledge base, and how are these things treated.
Yeah, maybe we can do the final steps. Tassos, if you stop sharing, I would start sharing again for the final steps. Great, thank you. And just to show the difference, if you start from within the knowledge base, then you have to upload the image first. It has to be associated with a particle, which has the advantage that you have all the information about that particle and what it is. And if you then go to process in NanoExtract, you will end up with a slightly different URL. And the only difference really is that at the bottom, where you have your results of your image analysis, you have a button upload to knowledge base. And that's only working if you really come from the knowledge base, because the tool has to know where the image is coming from and what it's talking about. So this analysis is the same as what Tassos has just been showing. It's all the same methods and steps there. And then in the end, you can actually push it back, the results, to the knowledge base. And what's happening there is, if I just go back, you have not only your process in NanoExtract, but you have your results that have been coming back. And going for the results, you can, of course, store multiple analysis results for one image, because you have used different settings and so on, as we've just seen. And then with your results, you have the metadata, so the parameters that you have been setting for this specific analysis, for this image, and then you have your analysis results, your circularity, your parameter, and so on. So that's, as Tassos just said, you can have multiple results for one image, and of course you can have several images for one nanomaterial. And what we're gonna do next is provide a possibility to select different analysis for each image and then calculate an average or something like that. And yeah, with that, your particle characterization would be directly available, and you could then make it public in the NanoCommons knowledge base.
Perfect. Thank you very much.
Maybe some question regarding the browser differences that we encountered when Tassos was doing the live demo. They depend then on which browser you also entered the NanoCommons knowledge base with, or how is this?
Yes, should be, because like the browser that you use to enter the NanoCommons knowledge base will be the browser that will open the tool. So these are always linked. And I see Dieter nodding, which is very good, always. So yes, so be careful. Yes, as I said, be very, very careful when it comes to browsers. So you saw that, you know, a bit up, a bit down. It will make a huge difference. May make a huge difference in your results. So I like using Firefox because I can see the full image zoomed in automatically, but I always verify the results in Chrome, because in this case, you know, I know that the image is going to be full size, whatever, no matter what. So as Dieter also said and agreed, the browser that you use to enter the NanoCommons knowledge base will be the browser that will open the tool. So yeah, that will also define how the tool will behave. The only way that you can change browsers, if let's say someone sends you a link, let's say into WhatsApp or Viber or whatever, and you click it, and then it will open with the default browser that you have in your system. But from then on, everything will happen with the exact same browser, because they are connected, because this is how the systems work in general.
And of course, I guess it needs to be said at this stage that as long as you're still playing with the tool on the way, trying to get kind of reasonable results, you do not upload, of course, to the knowledge base. So you would just then press the button upload to the knowledge base if you're certain then that you have generated sensible data somehow.
Yeah.
So it's not that everything is captured automatically. It's kind of, you really have control of to provide data that you're also standing behind.
Yeah. And as Andreas said in the chat, please feel free to get in touch with us if you need help with your image analysis, either through Andreas and Nova Mechanics, or through Dieter and the NanoCommons knowledge base and his team. In any case, the images will end up to us, and we will be more than happy to help you analyze your images and get you some good results back. So yeah, any help any help that you need is more than welcome.
Thank you very much, Dieter. Thank you very much, Tassos. This was very interesting. Of course, always a big challenge to do all these kind of things in real time. I hope it was also a big profit for all the attendees, and as Tassos and Andreas offered in the chat, things are going to be dealt with also in the future. So everything that went onto the drive is going to be looked at offline. Of course, it cannot be come up sometimes with really the most decent results in the end within this very short time frame.